You don't have to keep your camera on if you don't want to. I always like it so I can at least get to see who you are, but I know it's kind of day one, but we're just going to record just in case anyone is to miss. But hello, nice to meet everyone. My name is Alyssa Thomas Cooper, and I will be your instructor for the remaining semester. So I normally say welcome to biochem, but you've already had a few weeks. So welcome to the new start of biochem. Hopefully you guys have a really positive experience and you end up learning a great deal in this course. This week, I'm still just getting access to everything. So I now have access to your shell. I don't have access as of right now to your online homework for the Pearson portion, but I should have access by tomorrow. So I'm hoping that by Friday, I can actually get in and enter your grades via Canvas. So that way you guys can have a little more access to it. Plus, I'll be able to help you guys with navigation a little bit more as well from that aspect. There will be some changes to the Canvas shell, just as a kind of heads up in terms of due dates. So because of the transition, I'm going to sort of postpone everything a week. And we will have plenty of time to catch up. It won't be an issue. So basically, things that were due Monday are now going to be pushed off to the 14th. If you already have it done, excellent. If you don't, no worries. You'll have that additional time. So basically, everything will just sort of move down a week. I want to show you also as well where to get a hold of me. So that way, in case anything is to happen and you need to send out an email or contact me, you sort of know where to find things as well. So let's go ahead and go into the module really quickly. And you'll see where it says faculty information. So in the start here portion, you'll see faculty information. I have now changed that so that way you guys have my email address and you'll also have my direct phone number. So if for some reason you need to have a formal email sent out, you can reach me at atama07@baker.edu. I do check my email daily. So I always say with sort of the understanding that I'll get back to you within 24 hours. So I usually do check it more frequently than that, but I'll always promise I'll respond to you within the next day. If for some reason you need to contact me sooner, that is actually my personal phone number, and you can feel free to use it. You can text or you can call. If you do text me, just let me know your name and the class. Just say I'm so-and-so and I'm in biochemistry. And this is my question. So that way I can get back to you accordingly. I not only teach this class, I also teach microbiology out in the Owasso campus, and I also teach at Delta College. So I do not mind giving out my personal phone number. And like I said, you guys are more than welcome to use it. But just make sure I know who you are so I can answer. Because if you just say, when is this due? I have no idea who you are, and I'm terrible. I don't save numbers. So just make sure when you text me, just say, this is so-and-so, when is this due? Or I will be a little late to class, or I need some help getting into the Canvas portal for some reason. So if it's more informal, go ahead and contact me. Or again, if it's something that needs longer explanation, go ahead and call me. If it's something that needs to be more formal, then go ahead and email me. But otherwise, I mean, if you email me, again, it's not a big deal. If you call me or text me, it's not a big deal. Whatever you guys are comfortable with, I just like to give you that sort of window. I'm usually a lot quicker on my phone because I am switching from classes to classes. So I tend to check text messages and phone calls a little bit more frequently versus email. I usually check at the end of the night or right before class. You may not get a response as quickly as you'd hope versus text. I'm a little bit quicker. In terms of about me, I have a bachelor's from the University of Michigan in biology, human biology. My master's is also from the University of Michigan as well. And I am working on my doctorate right now in physical therapy. With that being said, I have taught at the collegiate level for almost 8 years with Baker College. I've taught several classes. So I think Dr. Flack even is always laughing about, I just am sort of the person that picks up classes wherever they need me. So I'll teach microbiology, pathophysiology. I taught chemistry for several years as well in the Flint campus. And if it's biology or chemistry related, I usually am somehow involved or teaching it or have taught it at some point in time. So if you have any other questions regarding biochemistry, I'm more than happy to help you with that. And if you have questions for other classes, feel free to reach out as well, and I'll do my best to help you as much as possible. So like I said, you are going to see some changes to the module, and I will pretty much, if I do make changes, I'll write it in announcements, and I'll also send it to you via email as well. So that way you kind of get a double hit, if you will. You'll see it posted on announcements, and you'll get a link to your Baker email in case I make some changes. I like to kind of keep you guys informed, so that way you're not freaking out at the last minute of kind of what's going on. So as of right now, we're going to, again, make sort of this today be over chapter 7. So your chapter 7 homework will now be due next week. Just as a heads up, I wanted to give you guys that a little bit extra time and to make sure that we're starting off on the right foot. Starting next week, we'll start working on chapters 8 and 9, and we will kind of go from there. And like I said, I would rather you guys have a good foundation and feel comfortable with the information before we move on. I know some of you guys probably are already comfortable with chapter 7, but maybe some are not. So I want to make sure that we're giving justice where justice is due. For right now, we're going to keep with that same PowerPoint that you guys have and just kind of continue through it. And we're going to do a lot of practice. So if you have your calculator handy, make sure you have a calculator, whether it be a graphing calculator, a scientific calculator, or your phone. We are going to be practicing a lot. And the best way to get through the first 8 weeks, because if you sort of notice how the class is set up, you get a really strong chemistry background in the first 8 weeks. Then it will move on to organic chemistry. And then we're going to end with more of the biological side, the biology, biological sciences aspect. So you're going to have a lot of mathematics behind it, a lot of equations to know, a lot of formulas, a lot of more math related pieces. Some of you guys may be really strong in math. Some of you may not feel as comfortable. So we want to make sure that we're constantly practicing. The best way to understand chemistry is just to keep doing problem after problem after problem after problem. It is not something that you can just look at the PowerPoints once and be like, oh, okay, I know how to do that. It's not one of those courses. It is one of those you just practice, practice, practice until you are very comfortable and feeling like you've really mastered that skill. So homework goes a long way, and it really is very beneficial and very helpful. And probably more than likely starting the next couple of weeks, I'll have it more set up to where you'll have actually time to practice more problems. For today, again, we're just going to kind of go through the slides, make sure we're comfortable with that information. And again, I'll give you guys a bunch of examples so you're practicing at home. And the best way, again, just to get the most bang for your buck and have the best efficient studying is that active learning. Write it down right along with you. Make sure that you are going through it. You're not just kind of sitting back and passively learning. For this class, it's better to have that active learning. Now, I will record lectures as long as everyone is comfortable with it. If anyone's not comfortable with it, I don't have to necessarily post them, but I do like to record the lectures because one thing, I do talk fast. I've been really trying to practice talking slower, but when I get excited, I talk fast. So I like to have the recording. Plus, some of you guys may be more of an audio learner and you do like to have that second chance to listen in. So I like to have that available. Canvas is kind of funny. It's very difficult to upload recorded lectures. So I will give you guys a Google Doc that you can go into and have access to at any time and watch those lectures over. So I'll have it posted in each module so that way you can go back and listen to it. But just to straight upload them, it's very difficult and tricky, and it just never ends up working out. So you'll have a Google Drive, you'll have like a Google set, so you can go back and listen to the lectures if you choose. If not, I know that there's going to be study groups kind of formed. I know some of you guys have already met with Dr. Flack. Whatever extra work you can do, it will be definitely beneficial. Now, while I have you guys here, are there any questions for me at this point in time? And you can either type it in the chat or you can shout it out. I don't mind either way. Any questions, concerns, comments?
I have a question.
Yes.
So for the homework, I understand that they give us like different opportunities to do each problem, but even though we don't, like, if we make mistakes on those opportunities, we don't get 100% on it. Is there any possible way they can change that?
As long as it's okay with Dr. Flack, I don't know what their standard is for that. I have no issue with it because to me, the way I look at homework is that it's practice. As long as Dr. Flack is okay with me changing that, I'll change it. And then that way you guys can go back in, do the practice and get the full points for sure. Because
Yes, I would really appreciate that.
yeah,
Because like with our statistics homework, when I had statistics, like we were able to redo the problem as many times as we could. And as long as we were able to get it right in the end, like we'll get full credit for it. And it's not like that with this homework.
okay, I'll see why. And like I said, that's something I'll have to ask Dr. Fleck. As long as it's not a Baker requirement, I have no issue with changing it because especially when it comes to homework, it's different when it's a quiz and it's different when it's an exam. That I will, you take the penalty for the wrong answer. But for homework wise, the whole goal is to have repetition and to learn from your mistakes because it's homework. That's the time that you do learn from your mistakes and you do try to struggle with it and practice and you won't always get the right answer. So I'm okay with changing that. I have no issue with that. But like I said, I will send that out the email to Dr. Flack just to double check to make sure it's not a standard for Baker. I don't believe that it is. So I'll, right after class, I'll shoot her out an email and I'll have a response pretty quickly. She's pretty fast. I'll probably know within like 15 minutes after class.
Sounds good. Thank you so much.
No problem. But like I said, as of right now, I still don't have access to the Pearson. It's sort of funny. I do for a different college, but I don't for this college. So they have to try to fix this shell to get me access. So like I said, I'm hoping, they said I should actually have it by tomorrow morning. Hopefully I'll have it sooner than that. But if not by Friday, would probably be the latest. And then I'll spend the weekend kind of going back in and checking things and making sure to give you guys that credit. And also again, to upload your grades as well, because I know that that's very stressful when you don't necessarily get to see your grade. It makes it a little rough. So we definitely want to know where everyone stands. I need to know where everyone stands as well. That'll help tremendously on my part. And also lets me know where you guys are kind of struggling as well, because maybe someone is really good at balancing chemical reactions, but they're not great with stoichiometry. Or maybe vice versa when we get into gases. Maybe someone's really great with like Boyle's law and understanding that sort of idea, but you don't understand partial pressures. So I need that as well, so I can see kind of where the discrepancies are too. So yes, great question. And like I said, I'll have a response for it pretty quickly. I have a hunch. Are there any other questions? And if something pops up, you can go ahead and write it in the chat as well. I do try to check the chat as we're going through. For this class, if you want to shout things out, that's completely fine. It's actually a little bit easier just because we'll be writing things as we go. And if I have a question or if I ask you guys a question, it's a little easier for you just to respond. But again, if you're in a situation where maybe other people are in the room and you just need a comment via the chat, that's fine as well. But all right, without further ado, then let's go ahead and get started with chapter 7. So I know you guys have kind of already started it, and this is the same PowerPoint that you guys have. So again, just to make your guys' lives a little easier on the printer aspect, we will go ahead and get started with this. And then that way you guys can follow along. All right, so chapter 7 is going to be about chemical reactions as well as thinking about quantities. And what we start off with is actually talking about the idea of a mole. So when we discuss the idea of a mole, it's sort of funny because we use terms like a dozen, we use terms like a bushel, we use terms like a ream, and they all make sense to us. We know if someone says a dozen, that means 12. Automatically, that's stuck in our brain. You're going to want to do the same idea with a term mole. 1 mole is 6.022 times 10 to the 23rd atoms of whatever substance that you're looking at. So to make our lives easier, when we discuss the idea of 1 mole, it's easier than constantly saying, oh, we have 6.022 times 10 to the 23rd. We have 6.022 times 10 to the 23rd. It doesn't naturally rattle off the tongue. So that's why we use the term mole instead. And it's sort of funny, actually, when I went to University of Michigan, there was a chemistry club that celebrated Mole Day. It's on 10/23, and they hid little moles all throughout the campus. And if you found all the moles, you got like a $50 gift card, or whoever found the most moles got a $50 gift card. But when you hear the term mole, again, you're going to think about it just as you were thinking about a case, a ream, a dozen. It has that equivalent, that 1 mole of whatever, 1 mole of aluminum, 1 mole of helium, 1 mole of argon is that 6.022 times 10 to the 23rd. And so again, when we think about this, it can technically be an item. So if I said I had a mole of popsicles and I had a mole of popcorn, it means the same thing. So when we think about that, if I said I had a mole of feathers and I had a mole of marbles, I have 6.022 times 10 to the 23rd marbles. I have 6.022 times 10 to the 23rd pillows or feathers, whatever it could be. So when you're dealing with small particles, because again, that number is giant. If you were to actually put out 23 zeros, that is a gargantuan number. And so it's very difficult to think in those terms. That's why the term mole ended up being used. And it was actually, the name of it was actually based upon Amedeo Avogadro. He was an Italian physicist. And so it's, again, just a nice way of looking at it. Now, you are going to become very comfortable with this. And if you are not yet, be prepared. This guy constantly pops up because sometimes we are going to want to know how many atoms we have of argon, how many atoms we have of oxygen. And we can use this equivalent to be able to get where we're going and to be able to configure back and forth. So if you're not comfortable and you don't know this yet, you're going to have this stuck in your sleep. Keep memorizing it. 1 mole, 6.022 times 10 to the 23rd, 6.02 times 10 to the 23rd. It will finally get there at one point. But that's the Avogadro's number that we were talking about. And so because of that, we can think about it in terms of atoms. So again, when we say that we have a mole of carbon, again, 6.022 times 10 to the 23rd, 1 mole of sodium, 6.022 times 10 to the 23rd. We have the exact same amount. Now, let me ask you this though, because again, if I'm telling you that it's the same in terms of item, does that mean that they necessarily weigh the same? Do they have the same mass? What would you think?
No.
No, they're going to weigh different. So again, bringing back that idea, if I had a mole of marbles and I had a mole of feathers, I have the exact same amount, but they don't weigh the same. So we are going to have to take into account their mass. And when we think about mass, we think about mass in terms of grams. But from this aspect, again, if you hear 1 mole, it's the exact same number of atoms of carbon, exact same number of atoms of sodium. So again, just getting that little additional practice in. All right, so now with that being said, we can use this as a conversion factor. So sometimes we're going to be asked for questions to be able to figure out or configure the number of atoms or particles. And we can also be asked the number of moles. So depending on what we need, we can use what is called an equivalent. And when we look at this conversion factor, depending on what we're looking for, we can either put particles on the top or we can put particles on the bottom. Vice versa, we can put moles on the top and moles on the bottom. Just as perhaps maybe you guys learned that there are 2.2 pounds in 1 kilogram, that is also a conversion. So I could ask you to find something in kilograms and you could do it knowing that there's 2.2 pounds in 1 kilogram. Vice versa, I could ask you how many pounds there are knowing this equivalent. Same idea and same concept's going to work here. So this is where a little bit of algebra is going to come in. So I have a kind of a special way of doing things when it comes to setting up these problems. Because a lot of times what I've noticed in teaching chemistry is it's not necessarily a problem with doing the math once it's already set up, but it's how to get there, how to navigate yourself through. So we want to practice the what are we starting with and what are we trying to find. And that's the big thing, is that being able to understand and read these questions to know basically what we're looking for, where we're going to go, and what's the equivalent. But when you see this equivalent here, again, we can be asked to find something in moles, and we can do that knowing Avogadro's number. Or we could be asked particles, and we know that, again, knowing that 1 mole is 6.022 times 10 to the 23rd. So we're going to be seeing this quite a bit pop up. Okay, so to start off with, if we were thinking about the number of atoms in 2.0 moles of aluminum, I'm going to show you how I set things up, and then I'm going to give you another example to do on your own. So just to start off with, if you're not extremely comfortable with setting up these problems, I like to start off with what we know and what we are looking for, and try to get some sort of direction as to where we're going to go. So to start off with, we know we have 2 moles of aluminum. So we know we have 2.0 moles of aluminum. We also know the equivalent. We know that 1 mole equals the 6.02, and I always say 6.022. 6.02 will suffice for right now, times 10 to the 23rd atoms of aluminum. So we know how many moles we're starting with, and we know this equivalent. Now, what we're going to do is we're going to try to figure out what the question's actually asking for. What is the unknown? And the unknown is that we want to know the number of atoms of aluminum. So now we can set up our problem. And the way to look at this, again, now that we sort of have our knowns and our unknowns, now we can kind of gather a plan as to how we're going to get there. So always start with what they gave you first, what you know. And we know that we have 2.0 moles of aluminum. Now, we don't want to stay with moles of aluminum. We want to get rid of that because we're looking for atoms of aluminum. So now what we can do is we can use that equivalent. So based upon this equivalent, what am I going to put on the top? Am I going to put the 6.02 times 10 to the 23rd atoms, or am I going to put the 1 mole? What am I going to do? What would go on the top here?
Atom, I guess.
The atoms, perfect. Because what we're going to try to do is we're going to try to cancel out those moles of aluminum. Very good. So you do 6.02 times 10 to the 23rd atoms of aluminum over 1 mole of aluminum. So how this is set up now is like a mathematical kind of algebraic equation. And the whole goal is that we want to cancel out the moles of aluminum. So now that we're left with is the atoms of aluminum. And from here, all we have to do is multiply by 2 to that 6.02 times 10 to the 23rd. So when we do that, what number do we get now? What would we get?
1.20 times the 24th power.
Good. So 1.20 times 10 to the 24th power atoms of aluminum. Does that kind of make sense? I'm going to look at the chat really quick. So in Zoom, there's a little button that gives you the thumbs up. If this doesn't make sense, let me know. If this does make sense, give the thumbs up.
Oh, okay, I do have a question. Okay,
Sure.
so the 23rd power, how come do you guys go up a number?
So what happens here is when you write in scientific notation. So if I was to put this into my calculator, you have 6.02 times 10 to the 23rd. When we multiply that by 2, what ends up happening is you would get 12, oops, pardon me. Let me change this really quick. You would end up getting something like this. 12.04 times 10 to the 23rd. Did you see something like that on your calculator by any chance? Did it look
I
like
did.
Yeah, so what you're gonna wanna do and why this will make life a little bit easier. In proper scientific notation, we want to make sure that we move this decimal. So now we want it to be where it's 1.20. And when we do that, when we change this scientific notation, it actually increases the power. So then you get times 10 to the 24th. Just as if I went the opposite way, let's just say this was 0.120 times 10 to the 23rd, like this. Again, I want to move this decimal, so I have just one number in front of that decimal. And because of that, it decreased the power by 1. So instead of being 23, it would be the 22nd power. Does that make sense?
Yes, it makes sense now.
Okay, good. Because I was going to say that ends up being kind of a funny thing. And also too, if you probably noticed for question format and like homework wise, they will always show it in this proper scientific notation. And so that's when you just have to be careful. And there is a method, depending on what calculator you use, that you can change it to be in scientific notation. I don't remember off the top of my head for like a standard calculator, but in a graphing calculator, you can actually go in and change it. So you don't have to deal with the switching of the numbers, but you always want it to look sort of like this format. Otherwise, if you see this like 12.04 or 0.120, you're going to just have to change it in your mind. Say, okay, I have to either increase the power by 1 or I'm going to decrease the power by 1. But this will be how, in especially for like test questions and homework questions, they will throw it in scientific notation. So just be careful with that. Otherwise, that can completely change your number and make something very, very different. So we don't want that to happen. All right, now let me give you guys another example. Okay, let me say there is, let's change this up just a little bit. What is the number of atoms in 6 moles of carbon? So now I want you guys to work on this just by yourself really quick. So I'm going to give you guys, let's see, let's do 2 minutes to work on this. So at 2:01, we'll kind of run through it together. And I want to see what number you guys get. So go ahead and work on that. Okay, did anyone come up with a number?
At 3.612 to the 24th power.
Perfect. So 3.61 times 10 to the 24th. And that would be your atoms of carbon. Let's check this to make sure this answer is correct. So first of all, again, if you're not super comfortable with setting these up, we're going to practice with the knowns and unknowns. If you are comfortable, continue with what you're doing. But for right now, what do we know from this little passage here? What is something that we know right off the bat?
We have 6 moles of carbon.
Good, 6 moles of carbon. And then we also know our equivalent, that 1 mole of carbon is that 6.02 times 10 to the 23rd atoms. And what is the question asking for? What are they looking for?
Atoms.
Yep, good, atoms of carbon, perfect. And like I said, once I have a stylus and writing, this will be a little easier. So I apologize. Usually my handwriting is not this atrocious, but it'll kind of show you what to do from here. So yeah, we want to look for atoms of carbon. So we start off with what we know. And then again, now we have a little bit of a guide as to where we're going to go. So we're going to start with 6 moles of carbon. And then we're going to say, okay, we're going to now try to remove the moles of carbon. And to do that, we're going to put the 1 mole of carbon on the bottom. That cancels out. Now we have 6.02 times 10 to the 23rd. And if you multiply it, again, depending on how you're going to see it, sometimes you're going to see it as like 36.12, 36.14 times 10 to the 23rd. But again, we want to change that. And if your calculator is already set, you're kind of in good shape. It'll pop up as 3.61 times 10 to the 24th atoms of carbon. And the reason that I like to write everything out too is because now, again, if you get stuck on your piece of paper and you're like, okay, what did I just do? Because this has probably happened to all of you at some point in time doing these conversions where you're looking and going, what the heck did I just write? It's nice to have things written out. So that way you can clearly see, okay, I made a mistake here. Oh, I was supposed to convert here. So I know a lot of you guys probably like to do a little bit in your head and like to kind of jump those steps. If it works for you and you're doing okay, continue on. If you're not, try this sort of method of slowly but surely working out these problems, and it will get faster and it will get easier. All right, how did you guys feel with those kinds of questions? Does that kind of make sense?
Yes.
All right, I'm going to flip the script on you just a little bit. So now what I'm going to ask you to do is find the number of moles in 8.4 times 10 to the 24th atoms of aluminum. So I still want you to find the moles of aluminum, but now it's going to be switched a little bit. Now, instead of looking for atoms, you're going to be looking for moles. So what is the number of moles in 8.4 times 10 to the 24th atoms of aluminum? All right, so same idea. We know that we have this many atoms. And we know that, again, if we can use that equivalent, that 1 mole is 6.022 times 10 to the 23rd, we're going to be able to search and find moles. So again, we know how many atoms we're starting with of aluminum. 8.4 times 10 to the 24th atoms. And again, we know our equivalent. Now, what we don't know is how many moles does that end up configuring out to. So now we're going to start with what we already know, what they gave us. 8.4 times 10 to the 24th atoms of aluminum. But now we're going to flip the script a little bit. What's going to go on the top and what's going to go on the bottom in this situation? We're starting with atoms and now we want to get to moles. So what are we going to do?
Yeah, atom
Moles
will
in
be
the
at the bottom.
I'm sorry, repeat that one more time.
The mole will be on top, atoms
Good.
will be on the bottom.
You got it. Perfect. 1 mole of atoms on top. And then you would divide by 6.02 times 10 to the 23rd atoms of aluminum on the bottom. Very good. So now in this circumstance, again, if you were to put it in your calculator, 8.4 times 10 to the 24th. And if you divide it by 6.02 times 10 to the 23rd, what did you guys get?
I got 1.395, so we'd round that to 1.4 and the 47th power.
All right, good. Now let's double check this really quick. So sometimes when you throw it in the calculator, it may come out a little bit funny. So I'm going to double check one more time. 8.4 times 10 to the 24th divided by, and if you put them in parentheses as you do it, it will make life a little bit easier as well. 6.02 times 10 to the 23rd. I got 13.95. Did anyone else get that as well? When you went to go throw it in the calculator?
Yeah, that's what I got.
Okay, so sometimes, and I'm just gonna say this for when you go to put it in the calculator, especially if you do it with your phone, it doesn't like scientific notation. It gets a little confusing. So if you put your piece in parentheses first, and then you divide it and do another parentheses around that piece, you should end up with just like an integer number. If you end up with the 46 atoms, I think something got flipped in there, and it sometimes will create that scientific notation to add those exponents together. So just be careful when throwing it into the calculator. And if you need help with that, I can help with you after. But it should be around 13.95 moles of aluminum. So now you can kind of see how we can flip it back and forth. And so, like I said, if you kind of have it set up to where you sort of know what you're looking for, you already know what the equivalence, you can now sort of make that direction as to where you're going to go. And so writing these out makes it so much easier and gets that practice kind of going in. So let's continue on. And if we need to do a little bit more practicing, we can here later on. All right. So now that we know the idea of the moles being that 6.022 times 10 to the 23rd, we also can now look at this in terms of molecular formulas. So down here, what we have is the molecular formula for aspirin. So what it's saying here is that you have 9 carbons, 8 hydrogens, and 4 oxygens. And so when we look at this, again, there are 9 atoms of carbon, there are 8 atoms of hydrogen, and there are 4 atoms of oxygen. But now we can look at the relationship between these atoms and moles. So now again, we can create an equivalent again, just as how we said that 1 mole was 6.022 times 10 to the 23rd atoms. We can now think about it in terms of moles as well. So this 1 mole has 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So we can now look at this from the molecular compound idea and be able to use this again to manipulate the equation. Because let's just say hypothetically, again, this aspirin is a molecule, meaning that it's made up of, and these guys are sharing bonds to make up this chemical formula. But if I just wanted to know the concentration of hydrogen, or if I just wanted to understand the moles or atoms behind carbon or oxygen, I can actually pinpoint that out individually, knowing this idea with this relationship between moles of the whole aspirin formula and the carbon, hydrogen, and oxygen. So these little subscripts actually help you to determine that relationship. Let me show you a little bit more here in just a moment. So again, thinking about those conversions. So here again, we're looking at the idea of aspirin. What this is telling you is that for 1 mole of aspirin, you have 9 moles of carbon. For again, 1 mole of aspirin, you have 8 moles of hydrogen. And for that 1 mole of aspirin again, you have 4 moles of oxygen. So now what this can let us do is look individually of how many moles are in this particular compound or in this particular molecule. And again, we're able to do that understanding this relationship between that molecular formula and looking at that subscript and determining the number of moles. So let's do another little practice problem here. Okay, so we want to look at the number of atoms, and this is a 2-part question. So the first thing that we're going to do is we're going to look at the number of moles, and then we're going to talk about the number of atoms. But let's continue for a minute. So how many atoms of oxygen are in 0.15 moles of aspirin? And again, because we don't necessarily know what the molecular formula of aspirin is right off the bat, they give it to you here. So this is a little bit of a tricky question, and there's two parts to it. So again, if you were at home by yourself, you may look at this and go, crap, because you're not given necessarily enough information, but that isn't true because we know equivalence. So again, this is where writing down what you know, where you're going, and what we're looking for makes a whole lot of difference. So we know that we have 0.150 moles of this compound here. We also know that for 1 mole of this compound for aspirin, we have how many moles of oxygen? How many moles of oxygen are present in this mole for aspirin?
4.
4, very good, 4 moles. But the question isn't asking for moles, it's asking for atoms. So what else do we know about atoms? For 1 mole of oxygen, how many atoms of oxygen do we have? Think back to Avogadro.
0.02 times 10 to the 23rd.
6.02 times 10 to the 23rd. Very good. Moles of oxygen. And so now we can start to formulate a plan, because it's not asking, because part of us, especially me, I read things fast and I try to get done pretty quickly. If I was just to look at this, I would say, oh, okay, I know the mole, I can convert those moles, but it didn't ask for moles. It's asking for the number of atoms. Open it, this should say atoms of oxygen. So we're going to have to do 2 parts to this. Our first step is to convert from the moles of aspirin to the moles of oxygen. And then once we're there, now we can convert from the moles of oxygen to the atoms of oxygen. So again, if you can identify your knowns, and again, we have to think about those equivalents. You may not have all the information, but again, now looking at it, you do, because we know those equivalents. And from there, now we can make this format of sort of where we're going. And so I don't know if you guys have noticed this yet, but in chemistry, it helps to have a nice scrap piece of paper with you so you can write things down as you go. And especially again, in the beginning, while you guys are still practicing these, write out as much information as possible, because when you go back to look at your notes when you're doing homework, you're going to be like, what the heck did I write? And it's really difficult to navigate yourself. So write yourself these clues and these sort of pathways to get yourself to be able to set up these questions correctly. And it is going to help, I promise you. So, all right, let's go ahead and actually answer this question. So we have that 1.50 moles of aspirin. And now we want to be able to get to the atoms of oxygen. So again, first things first, we have to start with this 0.150 moles of aspirin. But I don't want moles of aspirin. I want to first get to moles of oxygen. So what do I put on the top and what do I put on the bottom?
Is it the 1 mole on top?
So be careful. We want to do 1 mole, but think about if it's aspirin or oxygen. Which one do we want to get rid of? What do we want to cancel out?
We want to get rid of the aspirin, right? 'Cause we
Good. So
want
we're going to,
that.
you got it. So we're going to put the mole of the aspirin on the bottom. And then what would go on the top?
The oxygen.
Yep, very good. 4 moles of oxygen. Perfect. So that's our first starting piece. So now we've gotten to our part 1, and now we have to go to atoms. So where are we going to go from here? Now we have our moles of atoms because we've canceled out these moles of aspirin. So now I want to go from moles to atoms of oxygen. So what's going to go on top and what goes on the bottom?
bottom would be 1 mole of
Yeah.
oxygen.
Got it.
And then the 6.02 times 10 to the 23rd.
You got it. Perfect. And that'll say atoms of oxygen. Perfect. So now when you go to put this in your calculator, and again, to make life easier, I always write everything out because now you can see that, okay, my moles of aspirin are canceled out, my moles of oxygen are canceled out. And so now all I'm left with is these atoms of oxygen. So now you can go ahead and type this into your calculator. So we have the 6.02. And I'm going to do things backwards because I have a rinky-dink old calculator. Ironically, my graphing calculator went kaput about 15 minutes before class, and I don't have AAA batteries. I'm like, really? It worked just fine yesterday. I even double checked it yesterday just to make sure. Nope, canceled right before class. So I'm with a nice little old-fashioned scientific calculator. So I have to do things kind of backwards in my own way, but it works. All right, so we're going to multiply that by 4. And then we're going to multiply that by 1.50. And what number did you guys get? So if you multiply the top, you don't have to really worry about the bottom. The 0.150 times 4 times 6.02 times 10 to the 23rd. What do you end up with?
Is it 2.40 to the top?
I got a different number, but we'll double check.
Okay.
Because
I
like I
got
said,
3.612.
that's what I got the first time, but I always double check because, like I said, when you get used to one calculator and you kind of switch over, it's like you're almost like I struggle with it, and I don't know why. I ended up again with the 3.61 times 10 to the 23rd. So if you want, and just to double check yourself, if you put in the 6.02 times 10 to the 23rd first and then hit enter, then multiply by 4 and then multiply by 0.150, you should end up with this number here. But we'll go ahead and double check to make sure that everyone got that. Did everyone kind of get the same number?
Yeah.
Okay, perfect. And like I said, some of this fun is just calculator funness. And if you guys notice, calculators are idiotic in some ways and some forms. It doesn't do what you want it to do. You know what you want it to do, but it inputs very differently sometimes. So depending on what calculator you're using, sometimes that'll also be like some little trials and tribulations to get over from there. But when in doubt, always throw everything in parentheses. It does help for sure. All right, so how do you guys feel with this question? This is a little bit different because it's 2-part. Do you guys want to practice another problem, or do you guys feel okay with it?
Can we do one more?
Sure, absolutely. All right, so let's now do it. Let's flip this up a little bit. So now I'm going to ask you how many atoms of carbon are in 0.150 moles of aspirin. So all we're changing is now, instead of looking at oxygen, now we're going to look at carbon. All right, so let's do this one again together. So we know that we're starting with this 0.150 moles of aspirin. And like I said, I always start with what they give us first, because that's kind of like your starting route. And then again, we can navigate through there using our equivalents. We also know that for 1 mole of aspirin, that we have how many moles of carbon? How many moles of carbon are we finding here? What was it?
9.
9, very good. And how do we know that it's 9 moles of carbon? This guy right here, that molecular formula. Think them through. As I say, you guys know it. We want to make sure that you can keep it, again, because when you go home tonight and you start practicing problems, you want to be able to rationalize in your head. The reason we know that is because that molecular formula, that subscript tells us that there are 9 moles of carbon for 1 mole of this aspirin. Good job, guys.
Okay, I just hesitated because I wasn't know if, I didn't know if there was more to like.
Nope, you're good. And that's, like I said, I always am going to ask you guys questions and you're probably not going to like it. But here's my argument, because I'm only with you a short period of time. And it makes sense when you do it in class. And I'm sure you guys have all had that too. You're like, okay, I get it in class. You go home tonight and you're like, what happened here? Like, how do we start this? And it's just rationalizing those pieces and making sure that, again, we have that navigation going through. All right.
Okay.
And then what else do we know for 1 mole of carbon?
It is 6.02 times 10 to the 23rd.
You got it. And that is going to be our atoms of carbon. So again, same idea. We are going to start with a 2-part. We first got to go from moles of aspirin to moles of carbon. Then once we get to moles of carbon, we get rid of that equivalent. Now we can get to atoms of carbon using that Avogadro's number. So now we got a plan. We know our knowns, we know what we're looking for, and we got a plan of how to get there. So I'm going to clear this really quick. And again, just remember that this is carbon. All right, so we have 0.150 moles of aspirin. And then I want to go from moles of aspirin to moles of carbon. So what goes on the top and what goes on the bottom? What would go on top and what would go on bottom if we're going to moles of carbon?
The top is 9 moles of carbon,
Got it?
and
Okay.
then the bottom is 1 mole of aspirin.
You got it. Perfect. And now what's going to happen is this is going to cancel out. So now what you're left with is those moles of carbon. All right, so now that we got the first step down, now we got to get to atoms. So what would go on top and what's going to go on the bottom?
I just have a quick silly question. I'm
Sure.
pretty sure this is the case, but the first 0.15 moles
Yeah.
or whatever, 150.
You-
That's essentially just over 1, right?
Yeah,
Like-
over 1, exactly. So yep, if you were, nope, and that actually isn't a silly question because that screws students up all the time. Yep, it's like
Okay.
saying over 1. Yep, you
Okay.
got it.
'Cause
No, not a silly
that's
question
what
because
screwed me up at first, and then I realized that I have to see it to.
yeah,
Okay.
if you see it and if it makes it easier, just set it up that way because basically if you're dividing or multiplying by 1, it keeps the same identity. But for purposes to like make this really like uniform, a lot of students have to put that over 1 to make it make sense. I actually had a student that had to keep it in brackets before because it wasn't like the multiplication was too like not clear enough. And so you're not the first person. Not a silly
cool.
question
Thank
at all.
you.
Nope, not a
That's-
silly question at all.
Thank you so much.
Absolutely. All right. So if we were going from moles of carbon to atoms of carbon, what goes on the top? What goes on the bottom?
Does the 6.02 go on the top?
You got it. Times 10 to the 23rd. Perfect. Oops. I gotta do this in a different color. 10 to the 23rd atoms. Good. Over 1 mole of carbon. Ah. See, this is where like having a whiteboard makes so much more sense. All right. So your moles of carbon cancel out. And now what you're left with are those atoms. So again, if we were to plug this into our calculator, like I said, I'm going to do things a little bit backwards. I'm going to put in the 6.02 times 10 to the 23rd first, and multiply by 9. And then I'm going to multiply by 0.150. And what did you guys get?
I got 8.12.
Yep, good. And now when we look at this number here, like I said, because I'm not sure how much background you guys had with scientific notation, because we're going to keep it with the 8.12, we'll actually round it to 8.13. We'll keep it as 3 significant figures right now or 2 decimal places behind. times 10 to the 23rd. I'm not picky about that necessarily for this class, but I know when you guys go to do that homework, they get picky. So I'm okay with it. Like, it's actually, for me, if you keep it, the more scientific units you go out, I actually think that that's more precise. And technically you would actually do 3. Oh, I took it back. Actually, you would do 3 because of scientific notation. I lied. This would be 0.12. Oh no, it would be 3 significant figures. So it would be 0.13. So it's 8.13. Sorry, losing my brain here for a minute. So usually you go with whatever the number states in scientific notation. This is 3 significant figures. So we'll do 3 significant figures down here. And because of that, then we round. Hopefully that makes sense. And if you guys need help with scientific notation or significant figures, just let me know as well. I'll try to catch everyone up on that too. But does this make more sense when you're running through these? Are these a little easier?
Yeah, it does.
Like I said, the biggest thing is to keep practicing with writing things out, getting sort of your navigational pathway, if you will, going with a plan, and then being able to tackle these, because they do get a little bit trickier as they go on, for sure. All right, let's continue on. So like I said before, when we think about moles, if I said I had a mole of oxygen and we had a mole of carbon, they're both saying that we have that 6.02 times 10 to the 23rd atoms, but they're going to weigh differently. And when we talk about weight, we're really thinking about mass. We're thinking about the actual amount of matter within it. And because of that, we're looking at mass in terms of grams. So they're not going to weigh the same. So a mole of oxygen does not have the same weight or the same mass as a mole of sodium or a mole of carbon. So we have to keep that in mind too. So now we're going to add in another additional foundational step. Now we're going to be thinking about mass. And when we discuss mass, we're going to be thinking about what we call molar mass. So when we think about molar mass, we are able to gather from the periodic table. And so the molar mass is the quantity of grams that equals the atomic mass. So if you have a periodic table with you, this will be a little bit easier. If you don't, you can grab one off of Google. And as long as you have a periodic table that shows you the atomic number and the atomic mass, this is going to make your life a little bit easier. In terms of if you have a textbook, because as I say, for this class, you should have a textbook. It may also have one in there for you as well to be able to go back and look at, but you want to be able to have one that has the mass numbers at the bottom. So this guy here is called the atomic number. And this tells you the number of protons in the element itself. It actually gives you the identity to it. But this guy tells you the mass number.
I actually have a question.
Sure, no problem.
For the midterm, will you provide us with a periodic table with the math?
Yeah, you'll have a periodic table for you. So,
okay.
And probably what I'll end up doing is just so that way everyone has the same one, I'll probably photocopy mine and then I'll just post it to Canvas so everyone can print it off. Because you will need this in order to answer some of the following questions.
Right. Yeah. That's what I was thinking. Okay.
Yeah, no problem. And like I said, for today, it's not necessarily a big deal. We'll kind of go back and forth. If you have your phone, you can pull one up. That would make life a little easier. Or again, if you have a periodic table with you, it's always nice to have on hand for when we discuss molar mass. So, and like I said, this is something that we're going to be looking at quite a bit to answer these questions. So the molar mass will be different for every element. They're all going to weigh something a little bit different. So here we're looking at sodium. Sodium has the atomic number 11, which actually tells us the number of protons. Now this bottom number, the mass, tells us the protons plus the number of neutrons in an average atom. And I'll kind of discuss that hopefully later on a little bit more, but this is going to tell you that mass. So if they're asking for molar mass, you need to go to a periodic table. So write that down somewhere. Molar mass, have a periodic table handy. And so sometimes it's going to be that we're going to look at the molar mass of just one element, or we're going to be looking at the molar mass of a compound in which we have to actually add up those numbers. And that gets a little bit more confusing and tricky, but for molar mass, need a periodic table, and it's got to have that that mass down at the bottom. Sometimes the periodic tables will look a little bit different. So some of them you'll see where the 11 is like up in the top corner. Sometimes it'll be on the top. That doesn't really matter, but you just want to make sure that, again, they have that mass number at the bottom. So very important to have. All right, so when we look at the molar mass, so this is of carbon. Again, when you're looking at this periodic table, the 6 is an integer telling you the atomic number. That tells you the number of protons that are in this atom. And if you change that number, you actually change the element altogether. So all of these elements are very unique in the fact that they have this atomic number. They have the same amount of protons, they function a certain way. But the mass number, again, is going to tell you this protons plus neutrons. And that's why it becomes an average. So we'll discuss again that a little bit more later on, but this is an average number. But this is what we know as the molar mass. So if you were looking at the molar mass of carbon, it's going to be shown as grams per mole. So grams per mole. And so here we would say that we have 12.01 grams of carbon over 1 mole of carbon. Now, again, because this is an equivalent, we can flip this back and forth depending on what we're trying to do and where we're trying to go from here. But for molar mass, again, you got to look at a periodic table to get that number. And it's kind of cute. I taught chemistry many years ago, but when I first started, like after I graduated from college, I started working as a tutor, and I tutored for chemistry. And I tutored this poor gentleman who I still talk to him to this day, but he passed chemistry with a wing and a prayer. And we were struggling because it was hard for me to teach him, and it was hard for him to learn because he didn't have a good math background. But what he did is he found this triangle, and he put that the molar mass was expressed in grams per mole. So if you were asked a question about how many grams were in a certain piece, you could use this triangle to manipulate it to know whether or not you were doing grams divided by moles or moles divided by grams. And I'll show you that later on. Keep that in your back pocket. It is actually very useful. My son, when he was in 7th grade, actually used this for class, for his algebra course. But for right now, we're going to be thinking about, again, that for 1 mole of carbon, it's this 12.0 grams. And again, we can say that there are 12.0 grams of carbon per 1 mole. That's our equivalent that we're going to see. And this is going to show us that molar mass. So on a different note, I'll show you guys that triangle, but it always makes me laugh to this day. It's been like 15 years and I still talk to him and we still laugh about it, but it worked out well. So again, everyone's going to have a little bit of a different molar mass. So if you were looking at carbon, it's 12.01 grams per mole. If you were to look at sulfur, it's 32.07 grams per 1 mole. And if you were going to then look at silver, silver is this Ag number. This would be 107.9 grams per 1 mole. So we're always going to be looking for the molar mass from the periodic table. And to help with rounding, we at least try to hit the hundreds place. So we always try to have another number behind it. So like 0.01, or we're going to try to use 4 significant figures. So if we looked here, this is 4 significant figures. This is 4 significant figures. And then this would be 4 significant figures. So just to make life a little bit easier when we see these numbers. Okay, so now again, when we think about these mole quantities, you're going to see that they look very different. So what they're telling you is that they have 6.022 times 10 to the 23rd atoms of sulfur, iron, sodium chloride, this calcium chromide, I think is what it is. And then we have some sort of organic compound at the end. But if you notice, all those masses are different based upon those elements that are found within. So this is going to be a little bit different. So the mass won't be the same, but the mole will tell you those numbers of atoms. Just like, again, if I said I had a dozen books, or I had a dozen marbles, I have 12 of them. That didn't change, but the mass will change. Same thing will happen here. So what we're going to do is we're going to calculate the molar mass of C2H602. So I'm going to help you guys out with this one because this is a little bit of a tricky one. What we first want to do is we want to just find the molar mass, and the molar mass is going to be expressed in grams per 1 mole, if you will. So what we need to do is we need to total up this number. And again, to total up molar mass, we need to have a periodic table. So we first have to find the molar mass of carbon. We got to find the molar mass of hydrogen. We got to find the molar mass of oxygen. Now, if you have a periodic table handy, again, this will make your life a little bit easier. For those of us that don't, we're going to use our phones and make this handy dandy. Although I knew I was teaching this today, you think I would have it up and ready to go, but alas, I don't. Doesn't always happen that way. All right, so grab your periodic tables. Again, you can use your phones, you guys can use the internet, whatever you got to do. But just make sure it has those mass numbers to help us out. Okay, let's see here. Finding one is going to be the fun challenge here. Periodic tables with mass. We have one here, perfect. Okay, so the first thing that we need to do is we need to find the molar mass of carbon. So if you look at a periodic table, the molar mass of carbon is going to be 12.01. But we have to be careful because how many carbons do we have in this little molecule, if you will? How many of them do we have?
2.
2. So we have to actually multiply this number by 2. Same thing then when it comes to hydrogen. If you look at the molar mass of hydrogen, it's 1.01. But now, how many times do we have to multiply this?
Times 6.
By 6, perfect. And then oxygen, if there's not a subscript, we automatically assume that this is a 1. So if it doesn't show you anything below it, it's just on its own. So oxygen itself will be 16.0. So when we go to look at this piece, and again, it would just be by identifying by itself. So we'd end up with this. Okay, so if we did 12.01 times 2, you end up with 24.02. And if we had our hydrogen and multiplied it by 6, we end up with 6.06. All right, so now what we're going to do is we're going to take these masses and we're going to add them up. So if you were to add 24.02 plus 6.06 plus 16, you're going to end up with 46.08 for the molar mass of this C2H6O here. And so what this is telling you is that you have 46.08 grams of this C2H60 or O over 1 mole of this molecule. So if it's just asking for molar mass, all we're doing is totaling up those numbers. Now, again, it's super easy to do if you just had carbon, but because we have a molecule, now we have to take into account how many of each piece do we have in order to make this happen. Does this kind of make sense? Again, if you can, use that thumbs up button or again, ask questions at this point in time. Are there any questions, concerns, comments on this? All right, I see a couple thumbs ups. If you don't, if this doesn't make sense, ask questions right away. All right, would you guys like to do one more? Just to get that practice in?
Yes.
Okay. So let's do, let me see if I have another one behind it. Nope. Okay. So let's do the molar mass of H2O. We're just going to make this simple and easy. So calculate the molar mass of H2O. And to make life a little bit easier, let's go ahead and I'll pull up the numbers for you. So hydrogen, if you were looking at the periodic table, would be 1.008 grams per mole. And oxygen, let's take it all the way out, would be 16.00 grams per mole. Sorry, let me give you guys a minute to work on it and then we'll meet together. Okay, so what did you guys get for the molar mass?
I got 18.02.
All right, let's double check this number and then we'll say grams per mole. Okay, so the first thing that you gotta do is you gotta do the 1.008 and we gotta multiply that by 2 because we have 2 hydrogens in this water molecule. And then you're gonna add it to 16.00. And if we do that, I believe that is the number. Yep, you would get 18.02 grams per mole. And again, when we write this, we're going to say that there's 18.0 grams or 18.02 grams of water over 1 mole of water molecules or whatever we may say. But it's going to be grams of water over the moles of water when we write this to make it a little bit easier. And like I said, when we express molar mass, we're going to say that it is in grams per mole to make life a little bit easier. And like I said, we can now manipulate this equation. So sometimes we're going to look for moles, sometimes we're going to look for grams, and we're going to know how to do this using the molar mass. So let's go ahead and try another little piece. So again, when we're looking at this conversion factor, now that we know that molar mass, we have grams per mole. And as I was kind of saying before, this is what one of my students used to use as sort of his little base, if you will. I don't like it because I like for everything to be nice and clear and very organized. But in case you're pretty strong with math, or again, just want to have a little extra piece, you can look at it from a triangle perspective. That molar mass is grams per mole. And so what you do is if you're trying to look for something, let's just say hypothetically, we're trying to look for grams. You cover up the grams with your finger and you would have molar mass times the mole equals grams. On the flip side, if I was looking for moles, I'd cover up the moles and it would be grams over the molar mass to equal the mole. So here is a way that you can do this pretty easily if you're trying to figure out pieces. And again, if we're trying to obtain the molar mass, it's in grams per mole. We got to use the periodic table. I had a student that he loved to do this. It made me crazy because this is just not the way my brain works. If your brain works this way, kudos, you have an easy shortcut pathway. I'm going to show you guys the long version because that's just what I do. What we're going to do is, again, now we're going to be setting up those same conversion factors because, again, now that we understand molar mass and we know that there are grams per mole, we can flip the moles and the grams depending on what we're searching for. So in this situation, we're looking at methane gas. So methane is actually pretty interesting. It is used in gas stoves and gas heaters. And actually, it's relatively pretty similar to the weight or the mass of water, but because water has hydrogen bonds, it's a liquid at room temperature versus methane is actually gas at room temperature. But when we total that up, so again, if we were to do the same idea where we look at the molar mass, you would look at the carbon plus those 4 hydrogen atoms and put that number together. So if you total this up, you would have 1 mole of methane equals 6.05 grams of your methane gas. And again, we get this molar mass from that periodic table. So we can use these pieces as conversion factors. So now what we're going to do is we're going to practice utilizing this idea between grams and moles and molar mass. So here we have a box of table salt, and it contains 737 grams of NaCl. And it wants us to get to moles. So again, I'm going to show you in both ways, although one way pains me. But if it makes your life easier and you can figure it out and have that conversion back and forth, more power to you. But what you can do is you can use that triangle approach and say, okay, it's looking for grams, it's looking for moles. We know grams. We can utilize the molar mass. So you can set up your little triangle. And because of the fact that we're searching for moles, if you stick your thumb over the moles, what you're going to do is say that the moles is grams over the molar mass, and to be able to figure out these numbers. Again, that's sort of the easy approach, but I'm going to show you the long way because I'm a chemistry teacher at heart. And if you like this shortcut, great. If it works for you and you understand it, perfect. If not, let me show you a little bit of the longer way to do this. Okay, so again, we're going to do the same idea of saying our knowns and our unknowns. Okay, let's do a screen. So we said that we knew that we had 737 grams of our sodium chloride salt, NaCl. We know that. We also can figure out pretty quickly the molar mass of NaCl. And the way that we can do that is by going to our periodic table. What we want to know, or what we don't know, that it asks for is the moles of NaCl. And the way that we can get there is because we can use that molar mass as grams per mole as our equivalent. So we can say that 1 mole of NaCl equates to this many grams because of the periodic table. So really quickly, let's go ahead and figure that out on the periodic table, the amount of grams that we would have for that molar mass. Okay, so really quickly, if we look at our periodic table, we'll see that if we're looking at this molar mass, sodium has a mass of 23.00 grams per mole. Plus our chloride has a mass, I believe it's 30.45, if I recall. Yep, 35.45 grams per mole. So we can total that up and get 23 plus 35.45. That would give us the molar mass of this NaCl. So now we know that we have, again, starting with 737 grams of NaCl. That's what we have. They want us to figure out the moles of NaCl. And again, we can do that because we know the molar mass. So what we're going to do, and this looks a little bit kind of a little shady. So let me go ahead and fix this really quick. All
I
right.
just have a quick question.
Yeah, no problem.
For chlorine, we wouldn't round it to from 35.45 to 35.5.
So it depends on the situation of what it's asking for significant units. Oh, I guess you would do 35.5 because it's asking for 737. So I apologize. That would be 35.5 because we're starting with
I
3.
just want to make sure so we always will round then for this.
Yes, you will round. So whatever your starting material is, go with that amount of significant figures to make life easier. That will
Okay.
just help as we start to run through these.
Okay.
So we know that we had the 737 grams. And again, we know that our molar mass is going to be did I say it was 58.5 grams of NaCl over 1 mole. So that's what we know. And now what we're looking for is the moles of NaCl. So that's what we're trying to figure out. So we'll start with the information that they gave us first. So we'll do 737 grams of NaCl. And now using this molar mass, we're going to try to get rid of the grams of NaCl and leave it with the moles. So using this piece here, what goes on the top and what goes on the bottom?
So the 58.5 grams of NaCl would be at the bottom.
Yep, you got it. Perfect. NaCl over 1 mole.
And those would cancel each other out, right?
You got it. Perfect. So this would cancel and this would cancel. And now all we have to do is divide 737 divided by 58.5. And now our number will be 12.6 mole NaCl. So we're going to practice this one again, but at least it kind of shows you again how I sort of format things. That way you can kind of see what's canceling out and what you're sticking with. And I think this helps a lot to kind of have, again, where you know what you're doing, you find the pathway, and then again, we can solve for our unknown a little bit easier. All right, let me give you another example. If you guys are writing this, I'll give you a chance to write it, and then I'll give you guys another example here in just a moment. And like I said, I am recording. I try to not write super fast, but I talk fast and I write fast. So I'm a little bit better on here because normally when I do my whiteboard, I race really quickly and I'm always told, stop. So I'm trying to be a little bit slower so you guys can keep up. But like I said, if not, it's always recorded so you can rewatch it when you need to. Okay, so let's go ahead and try another approach. Okay. So it says a sample of water has a mass of 59.8 grams. How many moles of water are in the sample? So it's kind of perfect that we just found out the molar mass of water not too long ago. But let's again start with what we know, like figure out our equivalent, and then again, what we don't know and what we're looking for. So what do we know from this piece here? What did they give us in this little scenario?
The mass is 59.8 grams.
Yep, good. And that's the grams of water. And we can figure out the molar mass pretty quickly of water. And again, the molar mass is going to be grams per mole. And we get that from the periodic table of elements. Now, it just so happens that a few questions ago, we figured out what the molar mass of water was. Did anyone write it down? So that way we have it.
I guess it was 18.02.
Yep, good. See, this is why active learning is so useful. So now we have that and we don't have to go through the whole song and dance. But if we needed to, again, you find out the mass of the hydrogen. And when we think of water, again, we'll look at it as H2O. So we would have 2 hydrogen atoms that we'd have to account for, and then that 1 oxygen atom to figure out the molar mass. So we now know these pieces. And now what we don't know, and what are we looking for? And so what is it asking us for? What are we trying to solve for at this piece here?
The moles.
Good, the moles of water. And so remember, when we look at this molar mass, this is the grams of water over 1 mole of water. So now what we can do is we can formulate a plan. We can start with grams and go to moles by dividing by that molar mass. So we can convert from grams to moles pretty easily now, knowing this situation. So let me go ahead and actually clear this really quick. Like I said, I always like to set it up the same way. What your kind of equivalent is, or what like sort of our setup will be. And again, what we're really looking for, because as long as you know what we're looking for, we can make that clear path. Okay, so we're gonna start with this 59.8 grams of water. And now knowing that equivalent, we have grams and moles. So are we gonna put moles on top, or are we gonna put moles on the bottom? What do we wanna do here?
Moles on top.
Moles on top, 1 mole of water. And now we can divide it by that 18.02 grams of water. Now, again, because it started us off with 3 significant figures, we'll continue on with the 3 significant figures. So now all we have to do is cancel out our grams, because now we have moles, and now we can divide 59.8 divided by 18.02. And I got 3.32 moles of water. Does this kind of make sense how they're set up? Is it getting a little easier to see with more practice?
Yes.
Like I said, these are not problems that you'll do 2 and you'll remember them next week. They're going to take practice and just time and time again. But at least now you can see it kind of what to do when you get home and you're practicing these by yourself. You can kind of have that step by step as to what to do and sort of where to go from there. And I think this will make life a little bit easier as well. I think it turned it for the 58.5. I think it stayed as 58.5 because we rounded it up, if I recall. Sorry, I'm just checking the chat right now. It should stay as that, because I think it would have been 58.45, and then we just switched it to 58.5. And then same thing here. Again, we'll stick with that 3 significant figures. So then we'll just have that at the very end as well. So hopefully these are getting a little bit easier. And again, the more you practice, the easier this will go. So what I would suggest doing is tonight, before you go to bed, go back through your notes and try to redo these problems. I know it sounds funny because we already did them, but even just looking at them tonight and having that little additional practice, even if it's only for 15 minutes, when you go back tomorrow to work on this, or you come back on Friday, whatever it may be that you end up hitting this, it'll make it a little bit easier just to keep having that same repetition over and over and over, because we can change any number here. We can make it 90 grams. We can make it 195 grams. Doesn't matter. The setup will be the same. So don't let the numbers intimidate you. Think more about, again, how do we get there? How do we navigate our way through? Okay, so now that we see all these pieces, we've now talked about the idea that we can talk about molar mass. We also mentioned the idea with Avogadro's number, and we mentioned the idea of moles. So these are some of our maps that we can use in order to sort of navigate our way through. Again, if we start with grams, we can get to moles using that molar mass. And we know how to deal with moles to atoms because we have that Avogadro's number. So this is a nice little navigation tool. I would suggest actually printing this out. So I never really suggest printing out PowerPoints and large giant pictures, but if you can single this one out and just print this out, this is a good little roadmap to figure things through of where we're going to go from there. So again, you can go from grams to moles utilizing that molar mass. We can go from moles to atoms utilizing Avogadro's number. On the flip side, we can go from atoms to moles utilizing Avogadro's number. And then we can go from moles to grams manipulating that molar mass. So this becomes very useful. So like I said, I would take a moment if you can, if you're on campus today or if you're at home, you don't have to make every PowerPoint very big, but just isolate this one and print this one off. It will help you so much to have this little roadmap with you when you're doing your homework and going through those problems for sure. So I always suggest it. All right, so now we're going to take a little bit of a turn. Really quickly though, it is 3 o'clock. So we've been sitting for quite a bit of time. We're supposed to be on till 4, so we have a whole nother hour to go. But let's go ahead and take a 10-minute break. So I'll see you back at 3:12. Just take a moment, kind of refresh. If you guys have any questions, I'm going to stay on, but I want to give you guys a minute to move around a little bit as well. So I'm going to stop the recording just for resuming the call. Okay, so hopefully you guys had a little break to be able to run through everything. I now just got my other cup and drink, so we're good to go. It's funny, I don't drink coffee. This is actually Diet Coke. I have a really bad addiction to Diet Coke and I drink a 2-liter a day. So I'm trying to calm that down. So I try to flip in between water and Diet Coke, and I just keep the same cup. It's really gross, but anywho. All right. So hopefully this is making a little bit more sense. And like I said, you guys can go ahead and practice those. Again, take your time, work through them, go back and watch the videos. Hopefully this will make it a little easier when you're running through some of those problems. All right, we're going to start on a totally new subject now. Now we're going to be thinking about chemical equations. And we're really going to be now thinking about the idea of reactants and products and how we bring this all together to utilize this in sort of a chemistry format. So the first thing is you have to know how to write a chemical equation. So what you're going to see is that you have reactants on one side, and reactants are your starting material. Then you're going to see an arrow, and that's going to depict yield. We don't utilize or we don't use like a equal sign because it's not equal. It's showing you the direction of the reaction. And then it's going to show you your product. Your product is your end material. So you're going to see your reactants, your starting material. You're going to see an arrow depicted to show yield. And then we have our products at the end. And sometimes you're going to see that there's a delta sign. The delta is like a little triangle, and that indicates that heat was used during the reaction. So what we're going to talk about is the fact that basically what we start with should still be present in the product, but it's going to be rearranged. So therefore, if you had carbon in your reactants, you're going to end up with carbon somewhere in the products. But this may be in the form of CO2, it may be in the form of methane gas, but we've never created or destroyed anything in this process. We're just going to see that we're going to be doing some rearranging. And we also may show physical states too, because when we discuss matter, matter can be found in a few states. We can think about solid, liquid, or gas. And sometimes we also show AQ as well. And what AQ means is aqueous, meaning that it was dissolved in water. So we put that substance in water, and now it's actually broken apart into this aqueous solution. And so again, when we look at the chemical equations, we're going to see reactants, arrow, products. And again, we can show their different states, solid, liquid, or gas, or again, whether or not they've been dissolved in water, which we call aqueous. So this just shows you those different pieces to see and kind of helps you again understand what is being written here in this point. But we have to know how to balance equations. And so some students hate this. I think this is so much fun. And I will show you guys how much fun this will be in some way, some form. But like I said, atoms are neither gained nor lost. what you're going to see is that we have hydrogen atoms on our reactant side, our starting material, and we're also going to see it on the product side. It's rearranged differently. So H2 is not the same as H2O. H2 is a molecular gas. It's called molecular hydrogen. And H2O is our water in the form of a gas state. So you're going to see that they're arranged differently, but whatever we start with on one side, we have to have on the other side. So we want to make sure that they're balanced out. So this is why it's so important to balance chemical equations. And so what we're going to just do here is we're just going to state the number of atoms of each element on the reactant side and on the product side. And we want to make sure that we have the same amount. And this is where, again, if you like puzzles, you will love this and find this so much fun. If you're not a puzzle person, bear with it for the next week or so. But all right, so what I like to do is I like to make a little line. So I know that this is my reactant side and this is my product side. All right, here I'm looking at this P. P is going to stand for our phosphorus. How many phosphorus do I have on my reactant side? Does anyone know?
4.
4, very good. That subscript depicts that there are 4 phosphorus. On the same token over here, on our on our product side, how many phosphorus do we have? Right here. So if you see that coefficient out in front, imagine that you're multiplying it to that number. So if we don't have any subscript below, so it's just like 1 phosphorus. If we multiply that by 4, how many phosphorus do we have?
4.
4, very good. All right, let's do the same thing for now our bromine. So here we do see that we have a subscript and we do have the 6. So what we're gonna have to do is we're gonna have to multiply these. So how many bromine do we have on the reactant side?
12.
And on the product side, again, we have that 4. Not only does it go to the phosphorus, it also goes to the bromine as well because they're connected. So how many bromine do we have on the product side?
12.
12, very good. Is this a balanced equation?
Yeah.
And we're good to go. All right, let's do the same thing at the bottom. We've got aluminum, we've got iron, and we have oxygen on the reactant side, and we have aluminum, iron, and oxygen on the product side. So looking here on the reactant side, how many aluminums do we have? So over here on this reactant side, how many aluminums do we have?
2.
2, very good. This S depicts that it's a solid, but because we don't have any subscripts, just imagine that it's a 1. All right, now if I'm looking at iron, there's nothing out in front. So again, imagine that this is a 1. How many irons do I have here?
Just 2.
Just 2, very good. And then if I was looking down at my oxygen, how many do I have here?
3.
3, very good. Don't let this confuse you. The subscript just goes to this guy here. So here and here. But if it's a coefficient out in front, it will go to both. So now let's look on the product side. I like to just keep it in order. So again, because of how my brain works, I like functional and organized, and I like things to be neat and organized when I go to look at these numbers. So now here I'm going to look at aluminum. How many aluminums do I have on my product side?
2.
2, very good. There's no coefficient out in front, so we just have the 2 from that subscript. How many irons do I have on my product side?
2.
2, very good. And then how many oxygens do I have on this side?
3.
3, very good. When I look at this number, do I have a balanced equation?
Yes.
Yes.
Good. All right, perfect. This is exactly what we are going to do when it comes to actually balancing equations. So what they do here is they give you a little piece and they just tell you what's basically going to take place. So it says balance the chemical equation when solid Fe3O4 reacts with hydrogen gas. When you hear the term hydrogen gas, it means H2. To produce, and that produce is telling you that yield sign. A solid iron and water. So for right now, we're not going to worry about the states, like whether it's solid, liquid, or gas. We're just going to worry about actually balancing these equations. So basically how it's going to look is that we have Fe3O4 plus H2. And again, it says to produce. So we're going to show a yield sign, solid iron, which is going to be Fe, and water, H2O. All right, so right now, nothing is balanced. We are going to actually be the ones to balance them. So just as we did before, we are going to make our little line. We're going to set up that we're going to try to figure out our irons, our oxygen, and our hydrogen on the reactant side. And then on the product side, we're going to do the exact same thing. So we want to try to balance them out. Okay, so first things first, on the reactant side, how many irons do I have? How many of these Fe's do I have?
3.
Very good. So if you notice on the product side right now, how many irons do we have on the product side?
1.
1. So this is not balanced. So what we're going to do is we're going to balance it. What we have to do is we actually have to put in coefficients. So what we're going to do is we're going to place a number out in front. We can't put anything as a subscript down below, just to kind of like work our way through, make it easier on us because it changes the element. But we can add a coefficient out in front. So now how many irons do I have on this product side? If I added that 3.
3.
3, very good. So now that's balanced for right now. All right, now let's look at our oxygen. How many oxygen do we have on this reactant side?
4.
4, very good. And right now, if we were to look at oxygen, how many do we have?
1.
1. So again, same thing, not balanced. So I would love to just do this, but I can't because there's no such thing as H2O4. That doesn't work. We would change and not be water anymore. But what can I do instead? What can I put out in front?
A 4.
A 4, very good. It's called a coefficient and we can put it out in front. So now how many oxygens do I have on the product side?
4.
4, very good. So now it's kind of making sense. Now what we're going to do is now we're going to look at our hydrogen. So over here, how many do we have on the reactant side right now?
2.
2. But because I changed this number here and I threw this coefficient out in front, how many hydrogens do I have on my product side?
8.
Very good. So again, I can't change this to be H8. That's not a thing, but I can do something else.
I
What
have
can
a
I
quick
do?
question.
Yeah, no problem.
I'm sorry to interrupt.
No, you're fine.
And like, so you would never do a coefficient in front of the oxygen?
No, so because this is considered to be a molecule altogether,
Uh-huh.
you group it as if it's just one entity altogether.
Okay.
Yeah, that'll make your life easier because yeah, otherwise if you try to change it, it's now saying something different. Then you would have like
Okay.
hydrogen gas and 4 oxygen. So you want to make sure you just put it right out in front of the whole compound or the whole molecule.
Okay.
And that's a great question too, because like I said, sometimes you'll notice that people just will cheat and they'll try to like throw it in there. Nope, it's got to go out in front. And then it changed, and like if you notice, it now changed the number of hydrogen we have. So then to balance this, how many hydrogen and what can I do over on my reactant side to get 8 hydrogen and balance this guy out?
Put 4 in front of the H2.
Yep, throw a 4 in front of it. Perfect. And now I have 8. Perfect. So now I look back and this is why Like I said, I like puzzles and I like organization. And to me, this just looks so beautiful, especially if you line them up. I don't know, it's maybe my preference. It's not always everyone's preference, but again, I think this is very helpful, especially when you're practicing for these for the first time. It works to look at it this way. So you can see that you have the same amount of iron, you have the same amount of oxygen, and you have the same amount of hydrogen on both sides. So now we are considered to be a balanced equation. If you don't like puzzles, then maybe this isn't going to be the most fun thing. If you do like puzzles, you're going to get so used to them and you're going to really end up liking them. All right, so now when we balance, we also are going to balance what are called polyatomic ions. And so what ends up happening here is instead of breaking everything up into groups, let's just say hypothetically you had this PO4. If you notice, you have the same part over here. We, instead of breaking it up and looking at how many phosphorus we have and how many oxygen, we actually incorporate this together because this polyatomic ion is called phosphate. Now it's a little bit difficult because again, because I don't know what you guys had for nomenclature wise, this might be a little bit tricky, but basically what ends up happening is if you see that again, like kind of like they're in their same little group together, we'll keep them together when we balance the equation. So let me give you an example on this one. So we're going to do, and I'm going to write it on a different piece really quick. Na3PO4 plus MgCl2, Mg3PO4, 2 plus NaCl. We're going to actually do this on a separate piece. And again, we can follow them when we're going along with the notes. Okay, so I'm going to write this out really quick. You have Na3PO4, and this is called sodium phosphate, plus MgCl2, which is magnesium chloride. Again, this is our reactants. When we go to our products, we have that arrow that indicates yield, which means that we're going to make something new. And we end up with magnesium phosphate, Mg3PO4, 2, plus NaCl. So I have my reactants over here, I have my products. And as you can see, again, we have to come up with the same amount on each side. It's just how we assemble these pieces and these compounds that are going to look a little bit different. Okay, so over here, we're going to do the same sort of idea. We're going to set it up to where we look at our pieces and see how many we have on each side and try to balance these equations. But now, instead of it being that we're going to break up phosphate, we're going to actually keep it together in its same kind of grouping, if you will. So starting over here, if I'm looking at my sodium first, how many sodiums do I have on my reactant side? How many do I have over here?
3.
3, very good. Now on my product side, if I'm looking at sodium, how many do I have over here? How many sodiums do I have on that product side? Do I have a coefficient out in front?
1.
1. So now it's not balanced. But what can I do to get 3 sodiums on that product side? What could I do? Could I just go like this and call it a day?
No.
Nope. Unfortunately, that would mess it up. But what can I add out in front?
3.
I can add a 3 out in front. Perfect. So now I end up with 3 sodiums. Very good. Now, like I said, when it comes to this PO4, it's called phosphate. It's a polyatomic ion. And like I said, I don't know how much you guys got into anions and cations for the class, but we're just going to talk about the fact that it's going to be grouped together at this point. So when we look at our phosphate, treat it as if it is one entity. So how many phosphates do I have over on my reactant side? Do we see it in parentheses with any other subscript?
No.
Nope.
Well, 2.
So over here, like when we're looking at it, because it doesn't have anything below, on the product side, we definitely do. On the product side, we have a 2 for sure. Yep, you got it. But over here, we just have that 1. So we're just gonna call it 1. And like I said, this would be easier if I knew, but for right now, we're just gonna pretend like it's one big group and we'll call it a day. But now, as you can see, we're not even. So we have to do an adjustment. Now, what can I do over here that's gonna change this number up on the product side and the reactant side? I have 2 over here for my phosphate. How do I get 2 over on this side here? What would I have to do?
Would you put a coefficient of 2 in front of it?
Exactly. So now I can end up with 2 phosphates. But now what happened to my sodium number?
It went to 6.
It went to 6. And that's fine. But now we just got to play a little fixeroo on the product side, because now I only have 3 sodium. Instead of having a 3 out here, what am I going to put instead?
6.
6. Very good. All right, so now we have our sodium's good, our phosphates are good. Let's now look at our magnesium. So on our reactant side, how many magnesium do we have?
1.
1, very good. And then on the product side, how many magnesium do we have over here?
3.
3. So again, not balanced. We're going to have to go ahead and fix this. So to get 3 on the reactant side, what can we do?
Add a 3.
Yep, and we have to put the 3 out in front. So now I have 3 magnesium. But now let's look at our chloride. How many chloride ions do I have on the reactant side?
So we started with the 2, but since we added a 3, it would be a 6.
You got it, perfect. Because not only are you getting this going here, it's also going to go here. So when we do that, we multiply the numbers. Perfect. And then
I
if
have
we
a
go
quick
look,
question.
yeah, no problem.
So with on the reactant side with the, is it magnesium chloride?
Yep, you got it.
So we said 1, but I thought that magnesium chloride with the subscript of 2 would make it, I thought that was all 1.
So the magnesium just was 1 here. But because chloride has this 2 here, we have to take that into account, if that
Okay,
makes sense.
I thought, I don't know why, I'm probably just confusing myself, but I thought that the whole thing was looked at as one like entity.
So yep, so when we look at this piece here, you still have to look at the subscript. So that but so I now I get where you're going. So the polyatomic ions, that phosphate group is the entire entity, but the magnesium and the chloride won't be. It's just for
Okay.
that phosphate group that makes it funny. So I
Okay,
see
so
where the I
they're
see
all-
where the confusion is. So the
Yeah.
phosphate, because it has PO4 on one side and PO4 on the other, and they weren't separated, you can treat those as one giant entity.
Would it
Okay,
be would it be the same if we had nitrate and O3?
Yeah, exactly. If you had NO3, you would do the exact same thing. Or if you had nitrite, NO2.
Okay.
Yeah, and actually, I think we do have another example where we do sulfate. And so, yeah, they're set up that same way. So perfect. That's a great example. All right. So then when we go to look at this now, because does it now make sense why we have now 6 chloride on the reactant side?
yeah.
Okay, good. Well, now if we look over here, because we already did that work in the beginning, how many chloride ions do we have now on that product side?
6.
6. Perfect, because that 6 not only goes to the sodium, it also goes to chloride as well. So when we go to check our numbers, we're balanced. Like I said, I think these are super fun. You may not agree. I think they're cool. Once you get practicing with it, and like I said, because I just like the uniform of how to do it, I think this is easier than just trying to do it in your head, and then you don't really get to the chance to check them out. If you have it set up this way, you can see where your thought process went and where those numbers are kind of being swapped and being changed as well. So I think it's easier this way, but you'll have to let me know what you think. But all right, let's do some other examples really quick. Let's do A together, and then I will leave B and C for you guys to do on your own. So let me write this out really quickly. Fe2O3 plus C yields Fe plus CO2. Actually, let's do 2. Let's do A and B. We'll do them together, and then you can do C on your own. Okay, so really quickly, let me go ahead and get us off this piece here. Okay, so we have Fe2O3 plus C yields Fe plus CO2. All right, how many iron do we have on the reactant side?
2.
2, very good. How many iron do I have on my product side?
1.
1. It's not balanced. So what can I do to get 2 iron on that product side? What can I do to get 2 over here on this product side?
You add a 2 coefficient.
Yep, 2 coefficient, perfect. I can't just do Fe subscript 2, but I can put that 2 as a coefficient out in front. Very good. All right, now let's look at our oxygen. So over on the reactant side, how many oxygen do I have available? And this is supposed to be an oxygen. It's supposed to be my, oh, 3, very good. And now over here, if we look at our oxygen, how many are available?
2.
2, very good. So this one is going to be a little bit trickier. So because of the fact that it's not a clear-cut number, we're going to have to go by the, I think it's called the Coleman multiplier, if I remember, the one that you have to multiply them to get the closest number. So what we can do is we can actually add a 2 out here and a 3 over here. That's going to change some numbers when we do that, but we just have to be careful. So what did it change our oxygen to on the reactant side?
6.
6, very good. And then what did it do to the oxygen over on the product side?
6.
6, very good. But while this happened, it also changed my iron over here too. So now how many irons do I have on my reactant side?
4.
4, very good. And then just to make a simple switch over here, instead of this being a 2, we'll make this a 4. So very simple and easy to switch. All right, now we have to worry about our carbons, because how many carbons do I have on my reactant side?
1.
1. And then how many carbons do I have on my product side?
3.
3. I need a 3 to be over on the reactant side. So what can I do?
3.
Yeah.
coefficient.
Got it, 3 out in front. All right, am I balanced?
Yeah.
Yes.
Good. Do these seem easier?
Yeah.
I love them. I think they are so much fun. But again, I like the uniform. I like the writing. I use different pens when I do this because I am a nerd. You may not feel the same. But like I said, hopefully you'll think they're at least a little bit more tolerable versus before. All right, let's do one more. And then we will move on. Like I said, you guys can do that third example on your own. Okay, how many aluminum do I have on the reactant side?
1.
1.
1, very good. How many aluminum do I have on my product side?
2.
2. So I want to get, for right now, I want to get a 2 out in that reactant side. So what am I going to do?
Put a 2 coefficient.
2 of the coefficient, very good. All right, how many irons do I have on my reactant side?
1.
1. How many irons do I have on my product side?
1.
1. For right now, I'm good. It's subject to change, but right now, at least, again, we're looking to make sure we're balanced. All right, let's move on to our, oops, crap. I hate when it does this. Sorry, guys. All right, let me go back. Okay, how many oxygen do I have on my reactant side?
1.
1. How many oxygen do I have over on my product side?
3.
3. All right, so I'm going to have to change up some of these numbers because I want to get 3 oxygen over on that reactant side. So what can I do to get 3 over here?
Add the 3 coefficient.
Add a 3 coefficient. So now it changes that oxygen number. What else did it change in this process?
The iron.
The iron. So what can I do to fix it over here?
Add a 3 coefficient.
Good. And am I balanced?
Yep.
Perfect. like I said, I think they're fun. So hopefully one day you'll enjoy them as much as I do. But all right, so now thinking about different types of reactions. Like I said, what you start with, you're going to end up with in some way, some form. It's just going to be rearranged differently. So because of that, we have different classifications of chemical reactions. We have what are called combination reactions, in which we actually add our products together. Like if you had this and you add them together, we call that a combination reaction. We have decomposition reactions where it's the opposite, where we actually are breaking down the substances. We can have a single replacement in which we actually swap a component, and I'll show you that on a different format. We have a double replacement reaction in which we swap two components, and we have what's called a combustion reaction. So to start off with, again, just pretty simply and easy, combination reactions and decomposition reactions are the easiest to see. You start off with two things in combination, and in your product, you only end up with one. So they combine together to make this larger product. So again, we can see that we had magnesium plus oxygen gas, which we would say molecular oxygen, and it comes together to form magnesium oxide. Sodium plus our chloride came together to form sodium chloride. And then we have this sulfite plus water, and it comes together to make a sulfuric acid. So you can see that, again, you start off with two and you end up with one at the end of that product. So combination reactions are really easy to identify. Decomposition, it's the opposite. You start with one reactant and you split it to two. So down here we have our HGO. We can see that that's this mercury oxide or mercuric oxide. It'll split into being just mercury, and it will split into being oxygen. And then we also will see that, and I cannot think of what this is. I want to say that this is like potassium chlorite. I think it's potassium chlorite. It's so bad that I don't remember, but it's been a while since I taught that class. Believe it or not, it's like at this point, like 6 years ago, quite a bit of time ago. But anyway, you can see that it's getting split down into two substances. So decomposition and combination reactions are really easy to identify. Where it gets tricky, single replacement, double replacement, and combustion. Single replacement, you're going to usually see with two types of metals. So iron and copper, the Cu, are both metals. And what happens here is that they are going to swap each other out. So where you've seen iron on its own, it's going to take the place where copper was. So now when you flip it, copper is alone, and then Fe ends up going with this sulfate. So we have copper sulfate, and actually it'd be copper 2 sulfate. I'm sorry, iron 2 sulfate if we were to describe it. But you'll see that one element replaces another element. And again, usually it's two metals that are doing this swap. So you'll see that one metal is on its own, one metal is in a compound. And again, when they go to yield or make the product, they switch. So the iron will replace where the copper was, and the copper will replace where the iron was. So they call it a single replacement because you're just swapping out one metal for the other. Versus a double replacement, you're going to see that two things swap. So in this circumstance, we start off with silver nitrate, and then we have our sodium chloride. The silver and the sodium swap places. So now instead of having sodium nitrate, or I'm sorry, silver nitrate, we end up with silver chloride. And before we had sodium chloride, and now we have sodium nitrate. So two elements replace each other. So the single replacement just had one that swapped, the double replacement has two that swap. And so the same thing down here, we have our zinc sulfide, and then we have this hydrochloric acid. The zinc and the hydrogen swap each other out. And so now you end up with zinc chloride and this hydrogen sulfide gas. So you can see how they just sort of swap each other. To me, the double replacement and the single replacement are the hardest to identify. But again, if you kind of keep in mind that double has two and single only has one, it makes it a little bit easier to see. Then finally, we have what's called a combustion reaction. And what the only thing I will write to you guys, and this will make life so much easier, because combustion reactions come in all varying types, especially when we think about biological chemistry. We have combustion reactions that actually happen during our metabolism, but it depends on how quickly these elements swap components and how quickly they change. Because during our metabolism, we naturally are going to give off carbon dioxide as a gas, and there's no issue. Versus very quick reactions can blow up, and it has to vary again depending on the speed in which these guys change. But basically, what will happen is in the presence of oxygen, so you'll always see oxygen on the reactant side, you will create carbon dioxide and water. And so it doesn't matter what this guy is, but in the presence of oxygen, you're going to form carbon dioxide and a water. And again, this actually happens very naturally during our metabolism. When we think about cellular respiration, we take in glucose, we also utilize oxygen, and we end up breaking down CO2 as a byproduct, and we give off water and we get energy in the form of ATP. Again, this slowly happens so we don't blow up, but this can also happen very quickly and create a combustion reaction. So it has to do with speed in this case. But for a combustion reaction, just make yourself a mental note. In the presence of oxygen, so oxygen is a reactant, you will form carbon dioxide and water, and that will be your combustion reaction. So really quickly, let's go through and make sure we understand these guys. So they can either be a combination where you have two things that come together as one. You can have a decomposition reaction where you have you have one that's now going to form into two pieces. We can have the combustion reaction where in the presence of oxygen, we form CO2 and water. And then we can have that single and double replacement to which they're swapping components. So for the first guy here that we see, what kind of reaction would this be? So first of all, what's happening? We have aluminum and then we have this hydrogen. And if you notice, they swap each other out. So what kind of reaction would that be?
Single replacement.
Good, single replacement. All right, down here, again, we're going to see that we have sodium and we have the silver, and see how they swap each other out. So that way we end up with a little bit of a different structure at the end. What kind of replacement would this be?
Double.
Double replacement. Very good. All right, what happens in the third component? What are we seeing here?
Single.
Single replacement. Very good. And then finally in letter D, what's happening here?
Combustion.
Combustion. In the presence of oxygen, you form CO2 and water. And like I said, it always makes me laugh, and I always think about it because chemistry so many years ago, I had a student say, well, like, how do we not blow up? Because of the speed. Again, this looks the same as to if you were lighting a candle, if you had like some crazy bomb, that you can have a combustion reaction that happen very quickly, or again, it can happen slowly, which is what happens from a biological setting during our metabolism. So we go through cellular respiration. It's pretty nifty. See, I'm going to throw in some biochem in there as well. We'll throw some biology in there, bring it back to where we need to know it. Okay, so those are pretty easy. And again, that's just quick memorization. So what I would do personally is I would make some flashcards, make sure I know the difference between those different types of reactions. Not a whole lot to there to know. And like I said, keep balancing those equations. Make sure that that's feeling confident and feeling good. All right, now we also have to think about as well what are called redox reactions or oxidation reduction reactions. Very important in chemistry, but also very important in biology as well. So these redox reactions actually provide us with energy for food. So that's why, again, we're able to undergo the cellular respiration. It provides electrical energy in batteries, and it also occurs when you think about rust as well. So down here is actually a nice little example. So what you're going to see is iron. And it's going to combine with oxygen due to the presence of oxygen, and it forms this iron 3 oxide, which is going to be your rust. If you ever see some sort of metal in the presence of oxygen, it's going to develop rust in some way, whether it's aluminum, iron, nickel, they all kind of have that same reaction. But this is what you can see here happening as these redox reactions. Now, when we talk about oxidation and reduction electrons, or reactions, we're thinking about what's happening with electrons. And you can either have loss of electrons or you can have gaining of electrons. So when you lose an electron, you actually gain a positive charge. When you gain an electron, it has a negative charge associated with it. And it has to do with the atom. So again, if we think about in a neutral atom, you get protons that are in the nucleus, you got neutrons in the nucleus, and you have these electrons orbiting around. They have a negative charge associated with them. So the more electrons you have, the more negative you will be. The less electrons you have, the more positive you will be. And so this is where we really care about those oxidation and reduction reactions. So the way to remember this, and you can use two different forms. I remember oil rig. That was the way I was taught. That oxidation is loss of electrons. So therefore, again, you gain a positive charge. Reduction is gaining of electron. Therefore, you gain a negative charge. But also what a lot of students are taught is Leo the lion goes grr. Loss electrons, oxidation, gain electrons, reduction. So you may hear it back and forth in some format. Doesn't really matter. I don't care which one you remember. I remember oil rig, but if you remember Leo the lion goes grr, that's fine. So what they're showing you here is the difference between oxidized and reduced. So in this situation, what we're going to see is that the oxidized is going to lose an electron. The reduced is going to gain the electron. And so here they're just kind of showing you how that movement of electrons takes place. So oxidation is loss, reduction is gaining of electrons. So, and again, it just depends on which way you want to remember it. So again, why this is so important is it's not only important in chemistry aspect, but it's very important from a biological setting. So what they're showing you here is some examples between the oxidation and reduction of what's taking place. So originally we're starting with copper. And remember that if you lose electrons, you're going to gain a positive charge. So here what they're actually showing you is that copper gained this 2+ charge. And then we can see that we have these 4 electrons at the end. This is considered what's called an oxidation reaction. Oxidation is loss of electrons. In this circumstance, what we're going to see is that we had oxygen and it actually gained 4 electrons. So now it gained this negative charge. So now we have what is considered to be a reduction reaction. And so again, we can see how this takes place and how these variances between oxidation and reduction allow for these circumstances to take place. So now what can happen again is copper in the exposure of oxygen is now going to create this copper oxide, or what we would call copper 2 oxide. And again, that's going to form what we know as our rust. So very important from a biological setting, and again, very important from a chemical setting. All right, now one other thing that's not always made mention of, and I like to kind of talk about it as well. So let me go back really quick. From a biological chemistry perspective, let's just say hypothetically you've seen this, and then we go from here. Technically, if we were to see this, we would think about this being a oxidation reaction. Now you may say, how do we figure that out? Because this looks really funny and they're not the same components. What happens here is the fact that with oxidation, we actually lose electrons, but we gain bonds to oxygen in the process. Vice versa, if you gain bonds to hydrogen, you're actually going to go through a reduction reaction. So therefore, we could see something like this, and we would consider this to be a reduction reaction. So I just kind of like to make mention of that, so that way you can kind of see these pieces. And again, they do come up maybe for those of you that are going for undergrad and you're going to take higher level biology courses, you will kind of make mention of this as well. And again, it just helps from a chemistry perspective. All right, so looking here, what we're going to see is, again, we have silver and then we have this chloride. And under UV light, it initiates this redox reaction. So we end up with a silver that doesn't have that positive charge anymore. And now we have this chloride that doesn't show a negative charge at this point. So which reactant here was oxidized and which reactant was reduced? So remember, oxidized is loss of electrons. So which one lost electrons here? Does anyone know? It's a little bit tricky. So see here how we started with a negative charge and now we don't have a negative charge here anymore. What this is basically saying is that you have a 2 minus charge because of that coefficient out here. Now, when we look here, because we don't have any of those negative or positives, it's kind of just showing that it's neutral. So when we look at this piece here, these guys are the oxidized. So this 2Cl minus was oxidized. I know it's a little bit tricky to see, but it will get a little bit easier. On the flip side, we want to figure out which one was reduced. So starting here, we actually have a positive charge. And now because it gained electrons, now this one is going to be the one that became reduced. So the Ag plus ends up getting reduced just to regular Ag. Now, same thing here. If we're looking from this charge, this guy has a +2 charge. And now this guy, because now it grabbed those 2 extra electrons, now has a charge of 0. So remember, oxidation is loss of electrons. Reduction is gaining electrons. When you are oxidized, you lose that negative charge. When you're reduced, you gain that negative charge. So I hope that makes a little bit more sense when we go to look at these pieces. Let me give you another example really quick. I think I have another example in here. Oh, no, I don't. Okay. I'll have to look for another example for you guys so that way we're able to see these pieces. But all right, so again, just to kind of make sure we make mention of this, the oxidation is loss of electrons. And again, the reduction is going to be the gaining of electrons. Now I just looked at the time, it's almost 4 o'clock. We're not quite done here. We have a little bit more to go in terms of mole relationships. So what I'm going to do is I'm going to stop here from right now lecturing. What we will do is we'll pick this back up next week. But what I will do, so that way we can kind of keep on track, is I'll make a separate video for you guys of the last 20 slides. And then we'll just review them before we start carrying on. I want to make sure you guys feel comfortable with some of these pieces. So we stopped on slide, let me double check. We're stopping on slide 40. I will go from 40 and I will finish this up via a separate video. So that way you guys will have another video to watch. I'll make sure it's up. Probably it'll be up on Friday. So that way I just know where to go from there. And then we will do another review on Wednesday. And then again, we'll get ready to go into chapter 8. But from here,